So here is my sense amplifier circuit for SRAM, where we know that sense amplifier comes in the picture when we are trying to read, and during the read operation what happens is bit or bit bar, one of them goes to VDD or one of them stays to VDD, another one goes to VDD plus or minus delta V. We have seen that, isn't it? And we want to sense this difference, small difference in voltage compared to the other line. So one of them is at VDD, the other one would have a small variation or a delta V difference. So how does this operate? We have already seen. Let's quickly recap. When this difference is happening on bit and bit bar line, I'm not going into the details. At that point of time, my read enable is 0. So that means this is 0 and NMOS transistor is off. So my circuit, or there is no path of current to go to ground. So at that point of time, this difference is sensed. So here this difference would be finally given. Suppose this is 1.8 and this small difference plus or minus delta V, ideally it's not a plus, it's a minus only. When you have VDD by 2, you can have plus or minus. When it's VDD, it's a minus. So this small difference, this is 1.8, this is 1.6. And once this difference is sensed, after that you make your read enable signal 1. That means this transistor is on, this both are off. So no further changes or bit bar line are registered. And my circuit is nothing but as simple as this. This is my inverter, one inverter. This is my another inverter. This is my VDD. This is nothing but 1.8. If you see, this is the node. This is nothing but 1.6. They both are connected. And this is nothing but my ground. And this is read enable on, read enable high. So, and this 1.8 output of this is going to the input of this guy, and output of this is going as an input to this guy. So let's quickly name all the transistors: M1, M2, M3, M4 and M5. This 1.8 is coming from bit and this 1.6 is coming from bit bar. So we know that both of them are above or greater than 0.9, so both will be interpreted as a logic 1, which means that this one is going to this transistor, this output is going to this guy, so M4 is on, this output is going to this, so M3 is on. At the same time M5 is also on. So M4 on, M3 on and M5 on. So this is a closed switch. M4 try to pull its output towards 0 because NMOS is on. M3 is on, again it's an NMOS, so it's trying to pull its output also towards 0. Let's name the nodes. This is X and Y. So which will go first towards 0? See, we know that ID is proportional to VGS, correct? Here the gate voltage to one of them is 1.8, to other one is 1.6. So whoever has 1.8 voltage as its gate, there will be ID flowing faster and that node will go faster towards ground, because ID is able to discharge fast. So let's see, 1.8 is going towards M4, which is node Y. So M4 node Y and M3 node 6. So M4 will try, or node Y will reach 0.9 first. At that point of time, we have M3 or node X could be at 1.1. We have seen this in details in sense amplifier. And as soon as this goes slightly below 0.9, this will be interpreted as a logic value 0. That means Y goes to 0, which means that this 0 will turn on M1, M3 turns off, and X goes to a perfect value VDD. So I got Y from 1.6 to 0 and X to a proper value of VDD, which means my small difference on bit line is easily recognized. If I put the output probe here and here, here and here means on the bit bar line and on the bit line, I'll see that bit is VDD and bit bar is 0. The small difference got amplified. This is nothing but a differential amplifier, or the small difference got sense, which is nothing but a sense amplifier.